So hey everyone, welcome back to ML Works. In this video, we'll be discussing about quantization and we'll be talking about different types of quantization and we'll understand what are the different things that you can quantize in your deep learning model. So let's understand what is quantization first. So it is a model optimization technique that will reduce the numerical precision used for representing the weights and activation in your model. So consider you have trained a model, it will have parameters through which the model will learn. Now there will be hundreds of millions of parameters and each of these parameters is represented by a floating point value. Now instead of storing that floating point value in higher precision, which means like 64-bit or 32-bit to represent that floating point value, with the help of quantization, what we do is we transform that floating point value from higher precision to lower precision. For instance, if you see here, we have floating point value 123.123. Then we apply quantization, we transform that into integer 123. So when we do that, we reduce the amount of memory required for storing that specific value from 32-bit to 8-bit. That is reduction of 4x. So by doing this across millions of parameters, we drastically reduce the size of the model. So the key benefit is model compression and inference acceleration. So as I talked about this floating point to integer conversion, we reduce the model size. So since the model size is reduced, the amount of computation that we do during inference is also reduced. And since that computation is reduced, the amount of energy consumed is also reduced. So the key benefit or application of quantization is when you deploy this model on edge devices, it could be really helpful because edge devices have constrained compute available to it. So the model size should be less for deployment. And if you have a very large scale AI system, where you have thousands of GPUs for performing one inference, or even a large-scale AI system where you have millions of users concurrently hitting your endpoint, then you can use quantized model such that you can efficiently perform inference. So now let's understand what you can quantize. You can quantize the weights and activation in your deep learning model. So by quantizing weights, we'll be reducing the storage that is required for storing the model. And once the model size is reduced, automatically the time taken to load such a model is also less. Once the model loading is done, so what will happen is you will reduce the memory footprint when you are trying to perform the inference. And when you are reducing the footprint of the memory, the more memory is available to you. So what you can do is you can run multiple models as well. So that's what happens when you reduce the size of the model or you quantize the weights. So when it comes to quantization of activation, when you're performing training, you will be running through your layers of the neural network. So between the layers, you will have activations, ReLU activation or different types of activation that is happening. During the training phase, when you're performing the forward pass, you will be moving your tensors across the layers. Activation is one of the output in between the layers. So when you try to modify or turn from higher precision to lower precision, the amount of memory bandwidth that is available to you is more because you have less amount of memory consumed by lower precision value. So more memory bandwidth is available to you and the compute is also required is less for computing the low precision values. So by combining quantized weights and activation, which is the end-to-end low precision execution, what we do is we create an optimized hardware kernels to be used throughout the network, which results in maximum speed and energy efficiency. So by the end, what we'll have is we have smaller activation tensors and we can easily cache them and leading to faster inference as well. Now let's talk about types of quantization. We'll talk about floating point quantization and then we'll talk about integer type quantization. So in floating point quantization, if you just look at this image here, there are three components in a floating point value. One is the sign bit, then there is exponent and there is mantissa. So for float 32, you have one sign bit 8 bit for exponent value and 23 bit for mantissa. Now once you convert that into FP16 or BF16, the amount of bits available for exponent or mantissa is reduced, which will result in lower precision, but it will have a good range of floating point values available to it. So if you see the dynamic range, it tries to preserve that, and the real number structure, it will try to preserve those aspects. So what will happen by the end, right? You will be having a relatively high accuracy, and since it is supported by modern GPUs, it can run efficiently on that as well. So that is the point of floating point quantization, where we try to move from FP32 to FP16 or BF16. So BF16 is introduced by Google. It's called brain float 16. So basically what we do is we reduce the bits to represent the floating point value. That's why it will also affect the accuracy a bit compared to the original model that we train on. So when it comes to integer quantization, what we do is we map a real valued numbers, which is the floating point number, into a discrete number using a affine transformation, and it enables efficient inference using low precision arithmetic. So basically you have to perform two things. One is quantization using this specific formula. We'll talk about S and Z, what it is. Here we have talked about it. And once you do quantization, then you have to perform dequantization, for which you have this specific formula. So in dequantization, what we do is we do the reverse of what quantization does. So in quantization, we move to lower precision. With dequantization, we move towards higher precision. So here X represents the original float value of your parameter, and Q represents the quantized integer. S represented by the scale value, float value again. Z is the 0 point. So let's understand what is S and Z, because we know X and Q is original and quantized integer. Let's understand how these two parameters are used to reduce the precision of our floating point value from higher precision to lower precision. So parameter S represents scale and Z represents 0 point. So scale is derived from min-max float values of the tensor and min-max float value of the quantized range. Consider, right, you have a tensor, it will have a maximum value and a minimum value. So that represents the min and max of the float values of the tensor. And then you want to quantize them into specific range of integer, either it is 0 to 255 or minus 128 to 127. So here you have min max, again 0 is the minimum, 255 is the maximum. And again in this range, minus 128 is minimum and 127 is maximum, which is an int8 representation. So we use this formula to get the S value. And then for 0 point, what we do is we want to ensure how to represent 0. Whatever it is represented earlier in the float tensor, right? We want to represent it in calibrated format, in 0 point format here. So what we do is we take Q min, which is the quantized minimum, and X min. So we take these two minimum values and divide by S, and we get our 0 point. It represents the 0. So this process of determining appropriate scale and 0 point by observing the real valued data flowing through the model is called calibration. So this whole thing that we do, right, like scaling and 0 point detection, so both are applied on top of real valued tensor, and that is going through the model, and this whole process is called as calibration. Now let's talk about when quantization is applied. So there is post-training quantization and there is quantization aware training. And post-training quantization, it is applied on top of a trained model. You don't have to retrain a model to apply quantization. You just take an existing model, you apply quantization and reduce the size of the model. So the advantage is it is easy to integrate into existing workflow because you already have the trained model. And there is no need to modify the training code because we already have the model. So there is no need to modify the code to quantize, and it will dramatically reduce the model size and reduce the inference cost as well. The limitation is, since it is already trained, on top of which you apply quantization, it will directly affect the accuracy metric. And it is especially for sensitive models where you have this where certain models are highly sensitive to precision values. If you modify the precision, you will drastically reduce the accuracy as well. So it works best on models that are already robust to small numeric changes. So when it comes to quantization aware training, what we do is during the training process, while you're training a model, you apply fake quantization operation such that you will be reducing the size of the model or size of the operation that is happening, such that you are emulating the behavior of quantization during the forward pass by rounding off the parameter value or clamping down the parameter value. But when you are doing the backward pass, you ensure that full precision is available. Okay, this will enable the model to learn the robust quantization effects while maintaining the effective training dynamics. So this is basically during the forward pass, we apply quantization, and during the backward pass, we retain the full precision of the model. So the advantage is the highest accuracy among all the quantized models, and especially useful for smaller sensitive models that suffer from PTQ degradation. So post-training quantization, which suffer from some models like sensitive to precision. So it is better to use quantization aware training in such cases. So the limitation is you have to retrain or fine-tune the model, and it is slightly slower training due to adding quantization simulation. So basically, since we add this extra step, the time taken for training is also increased. So this is with respect to when quantization needs to be applied or where quantization needs to be applied. So what we'll do in the next video is we'll try to implement post-training quantization, and then we'll implement quantization aware training on a deep learning model. So with that, I'll be concluding this video. Thank you for watching.